Okay. Cool. Yes. Welcome again, everyone, to join this week's AI seminar at the USCISI. So today we are very happy to have Professor Zhiting Hu from Halicoglu Data Science Institute at UCSD. So Zhiting received his bachelor's degree in computer science from Peking University in 2014, and then the PhD in machine learning from CMU in 2020. So his research interest lies in the broad area of machine learning, artificial intelligence, and NLP, and also ML systems. In particular, he is interested in principal methodologies and the systems of training AI agents with different kinds of experiences, such as driven by data, symbolic knowledge, rewards, adversaries, and lifelong interplay, and also their applications in controllable text generation, healthcare, and other application domains. So his research was recognized with Best Demo nomination at ACL 2019 and the Outstanding Paper Award at ACL 2016. So today, Professor Zhiting, who is going to talk about text generation with no good data, reinforcement learning, causal inference, and unified evaluation.
Okay, yeah, thanks, Mohal, for introducing me, and thanks for inviting me here. I'm happy to share my recent work. Let me see. Okay, great. Okay, so this talk will be talking about text generation in the settings where you don't have so-called good data, right? Or even like you don't have any data at all. Okay, so we'll be talking about our recent work, kind of focusing on the fundamental techniques using like reinforcement learning, causal inference for handling these kind of cases, and we'll discuss a unified evaluation kind of protocol that we can use to like evaluate text generation kind of like models, right? Without requiring truth data, basically. Okay. So as we know, right, text generation has really, kind of achieve inspirational success, right, on many applications, like say language modeling, machine translation, summarization, right? In these cases, right, we usually have a lot of very clean supervised data, right? For example, GPT-3, right? You have billions of supervised tokens to train this large language model, right? And then we know that like speech recognition, machine translation, we have really achieved very impressive success, right, on many of the kind of like domains, basically, right? These are all kind of stemming from a lot of supervised data, right? But in many other cases, like we don't have access to for clean supervised data, or we even don't have any access to any data at all. Right, let me give you a couple examples. Right here, this application is to generate adversarial text examples. So here's a particular setting, right? For example, you have an entailment classifier, which is pre-trained, and you want to evaluate the robustness of this classifier, right? So entailment classifier is that it takes as input a premise sentence and a hypothesis sentence, and it wants to predict whether this hypothesis is really entailing this premise, right? Or maybe these two sentences are contradicting with each other, or they are neutral with each other. Okay, so to measure this robustness, we want to try to generate some hypothesis as a text, right? Such that with this attack as the hypothesis, this classifier will always output entailment no matter what premise you would input to the classifier. Okay, so this classifier is kind of confused completely by this particular attack. Okay, so for this kind of problem, we don't have any supervised data, right? We don't know like what kind of hypothesis can serve as the attack, right? and it's kind of impossible for human to write or to annotate this kind of attack, right? Because we don't understand this intermediate classifier at all, right? So this data collection is basically impossible through human. Another example, prompt generation, which is kind of a very hot topic these days, right, in NLP and in machine learning, right? Say you have a GPT-3 as the pre-trained model, and you want to generate or create some prompt to control the generation behavior of GPT-3, right? Here's an example, like with this prompt, say generate a story about cats. We hope that GPT-3 can generate a continuation such that this compose a story about the cat, right, of this particular topic of cats. Okay, then the question is, how can we automatically generate appropriate prompts so that this GPT-3 can generate whatever we want, right? Again, we don't have supervised data for training this prompt generator, right? And it's basically impossible for human to annotate or to write a lot of prompts, right? So that you can train a prompt generator, right, for given the tasks. Okay, so here's another example where this kind of no data issue prevents you kind of building these kind of generators. Okay, and yet another example is this very interesting problem of controllable generation. Right, say given a sentence, you want to rewrite this sentence so that this is you can change this sentiment, right, from positive sentiment to negative sentiment, right? Or you want to control the writing style by rewriting a sports commentary from a plain style to a more elaborate and flowery style, right? Again, we don't have a lot of such data, right? This period of data for you to train a model supervisedly, right, from input to output. Okay, and the final setting we'll be talking about today is like you have data, but this data is biased, which is really a common situation in practice, right? For example, this very popular bias, right? Like she is often associated with occupations like nurse, and he is often associated with occupations like lawyer or attorney, right? This kind of stereotypes or bias in the data, right? And the model tends to like inherit all these biases in the data and generates those kind of toxic or biased text, right, after training. So overall, right, we have seen a couple of examples in practice, right, where you want to build these generation models, but you cannot, you don't have access to data or high quality data, okay? But this problem, right, this low data problem is not only specific to text generation, right? Actually, in machine learning, a lot of problems actually face this kind of challenge, right? And in general, right, we hope that even though we don't have data examples, we hope to make use of other type of useful information, right? We know that those information can be stored in different formats, right? For example, this can be constraints or structural knowledge, right? We know in NLP we have these knowledge graphs, logic rules, right? These are all kind of structural knowledge. Or we can have like rewards from the environment, right? By interacting with the environment with human, we can get feedback, right? Whether this generation is good or not. Okay, and we may have other other models, right? Serving as an auxiliary agent, so you can co-train these models together, right? And these models share information between each other, or adversaries, right? Like in GAN, we have a discriminator as an auxiliary model to train the generator of interest, right? Or there can be combinations of all these experiences or informations, right, for a particular problem. And we know that we human, right, can ingest all this type of information, right? We can learn a new skill, or we can learn to complete a task by ingesting all information, right, from all these different type of experiences, right? But it's very hard for machine to make use of all these different type of information, right? These days, those successful machine learning stories, they basically, or are based on these data examples, right? With whatever like supervised learning, self-supervised learning, unsupervised learning, right? You always have to have data examples to train this model. Recently we wrote a paper about a more general paradigm of machine learning, where we call it we call it panoramic learning, to make use of all these different type of informations in a single learning algorithm. But this is not the focus of this talk. Instead, we'll focus on the text generation problem, and I will show some instances where we kind of use these fundamental new learning algorithms to enable the training of text generation, using all the other different type of information beyond the data examples. For example, the first part is about learning from rewards using efficient soft skill learning, an instance of reinforcement learning. Okay. Learning text generation from rewards, right? Again, let's see this example, right? We said that we don't have data to train this text, kind of like a visual example generator, right? To generate this text. But with rewards or reinforcement learning, it's possible to do this training, because we can easily create these kind of reward functions, right? Every time when you generate an attack, right, you can evaluate the success rate of this particular attack, right, and use this success rates as the one of the reward function. Okay, and you can use the reward function to supervise the training of the attack generator. And you may have a second reward function that you want to make sure this attack, right, this hypothesis sentence is a fluent sentence, right? So with these different reward functions, you can compose these two reward functions together and then run the reinforcement learning, right? I assume you know this reinforcement learning, right? This kind of you plug these reward functions into the algorithm, and you can train this text generator. Okay, so again, for the second case, right, prompt generator, similarly, right, with a prompt generated from your prompt generator, you can again evaluate the rewards of this for this particular prompt, right? Like say the first reward is that we want to make sure this continuation is really about this particular topic cat, right? So you can evaluate the topic classification accuracy, right? And second, you want to make sure this continuation, this story is a fluent story, right? A language is fluent, so you can again measure the fluency, and similarly you can compose reward 1 and reward 2 and run reinforcement learning. Okay, so reinforcement learning is a very general algorithm for you to plug in arbitrary reward functions to drive learning. Okay, as long as you can, devise appropriate reward functions, right? You can just plug in and compose, and then run everything to train the model of interest. And this reinforcement learning is very successful, right? It's a very fertile research area for robotic and game control, right? Like say those researchers, right? They train models or like agents to play these video games, right? This model is kind of generating an action, and this environment will translate to a new state and feedback with the rewards. So you can use this reward to train the agent, right, that controls the video game, basically. Okay, but unfortunately, reinforcement learning has a very limited success for training text generation. Right, there are a couple of key challenges for reinforcement learning applied in text generation. First is that this we have a really large sequence space, right? So this sentence space or text space is very large. Say you have a vocabulary size of 10 to 5, right? And you want to generate a sentence of length 20, right? Then this sequence space is this large, right? Which is kind of basically is extremely large. Okay, the second challenge is that this rewards is usually very sparse in text generation. right? You can only evaluate rewards after you see the whole text sequence, right? Like after you generate the whole text prompt or generate the whole adversarial examples, right? You can use that generated sample to evaluate those rewards, right? Reward 1, reward 2, and then you supervise the training, right? But this reward is very sparse. One sentence corresponds to one single reward signal. Okay, so this kind of challenges contribute to this limited success of training text generation. So next, let's dive a little bit more details into details, right, of text generation, so that hopefully this can inspire a new solution that solves the key challenges of text generation. Okay, so so as a background, right, we usually train text generation model as the autoregressive model, right? For example, given a sentence y0 to yt, right, this sequence of tokens, you have a model, right, a sequence model. Every time step you generate the token, right? Like say yt, okay, and for every step t, right, this yt the probability of yt will condition on all previous tokens, right? And in this model, you first compute the logic, right? And then you normalize it so that you get a distribution over the vocabulary, right? Conditioning on all the previous tokens, right? So f here is a logic. And then softmax is applied to normalize the distribution. Okay. So in reinforcement learning, right, all these concepts have a corresponding kind of term in RL, right? This sentence we say, okay, so it's a trajectory which we want to generate, and the YT, right, a new token generated at every step is an action, right? You will take this action AT. And all the previous tokens are seen as the states of the environment, right, ST. And this whole generation model is also called the policy, right, which is to generate a new token or new action given the previous state. Okay. So in reinforcement learning, right, every time when you take an action, right, or generate a token, you'll receive a reward, T, right? But as I said, right, this in text generation, this reward is very sparse. If the T is kind of like is intermediate steps, then usually this reward is just 0, right? Only after you generate the whole sequence, reaching the final step, you get a non-zero reward. Okay. And in RL, the general objective is that we want to maximize the cumulative rewards, right? We aggregate all the rewards along this sequence, right? And we want to maximize the expectation, right, of these rewards. Gamma here is a discount vector. So a key concept in reinforcement learning is the Q function, right? It basically measures the expected future rewards of taking action AT in state ST, right? So it's a kind of a core concept measuring the expected future rewards. Okay. And then previously people have explored RL text generation, right? With some interesting algorithms like policy gradient, which is an instance of on-policy reinforcement learning, where basically you apply this policy gradient to update the model parameters field, right? I won't dive into the details of these algorithms, but basically you can see, right? Here the procedure is basically you first use the language the generation model to generate samples from the policy, right? And then you evaluate the rewards or the Q values, right? And use that to update the model. But the problem is that this algorithm suffers from extremely low data efficiency because most of the samples from the model itself are just gibberish with 0 rewards, right? So this 0 rewards, basically this Q is 0, okay? Then this gradient is 0, right? It does not provide any useful information to update the model. So this training is very, very inefficient. There are other alternatives like off-policy reinforcement learning, like Q learning, right? It implicitly learns the policy by approximating the Q function, right? And how this Q function is learned, right? We have a very classical Bellman temporal consistency equation, right? Which says that this Q function must satisfy this particular relation, right, to be an optimal Q function. Then with this, a very straightforward everything is simply, we want to learn a Q function such that it really satisfies this temporal consistency, right? So again, I won't dive into details here, but it's actually pretty straightforward, right? You have this target, right? You use it as the regression target, and you train a Q function so that it can have the value, right, of this regression target, right? So that this Q function really satisfies this temporal consistency. Okay. So after learning this Q function, we can use the text generation policy, right? Every time we just pick the best token, right, that has the highest Q value, right? Or in other words, highest future reward, right? So that's basically the idea of Q learning. But the problem is that okay, this pipeline can be arbitrary policy. So it's called off policy. But the problem of this Q learning is that this training is really, really unstable because you can see, right, in this regression target, this target itself depends on the Q data itself, right? So it's kind of a bootstrapping. I use the model itself to supervise the model training, right? So it's a bootstrapping, which is known to be very unstable. And also because of the sparse reward, right? This RT at every step, if T is not the final step, then R is simply 0, right? So you don't really have any true training signals actually in this regression target, right? So this training is very unstable. And the second is that you can see this Q state, right? When you update it, actually it only involves the Q value of a particular action AT, right? Or particular token in the vocabulary. And we have a vocabulary size, for example, of like 1 million or like 100K, right? So it's very, very slow to like every time you update on the Q value for a single token, right? So you have to spend a lot of time to go through all these vocabulary size. So overall, right, with previous algorithms for text generation, with policy gradient and Q learning, you suffer from all these different difficulties: low data efficiency, unstable training, slow update, and also is sensitive to off-policy data. Okay, so these are the fundamental difficulties, right, that leads to the limited success of training text generation. Okay, so let me see if I have okay, so there's a question on the chat. The question is, classifier reward is sparse, available only when sentence completed, but fluency reward is not sparse. Yeah, this is a nice question. Yeah, this fluency rewards, right? You can evaluate this complexity every time you generate a new token. So fluency reward can be dense, but yeah, classifier reward is sparse. Okay, so but say you want to generate this adversarial attack, right? This classifier reward is a key reward. So that key reward is sparse. Okay, so with these key challenges, we want to see, is it possible to have a new reinforcement learning algorithm for text generation, right? So that we can alleviate those challenges and make it RL training more efficient and stable, so that you can really apply this RL to solve those problems of interest, like generating adversarial examples and prompt generation. Okay, so here's our proposal, solve the Q learning. So to introduce this new algorithm, perhaps it's best to put, soft Q learning and the hard Q learning, the traditional Q learning, side by side, so we can see what are the key differences, right, that really solve those challenges. The objective of hard Q learning, as we said, right, in conventional reinforcement learning, we want to maximize the cumulative rewards. But in soft Q learning, we cannot simply introduce a new entropy regularizer. Oh, by the way, soft Q learning is not what we invented, right? This is something already proposed in robotics community, right? They have been using soft Q learning as a more advanced techniques to solve other like robotic control problems. So we kind of introduce this algorithm to text generation problem. Okay. So the key thing, a new thing here is that we introduce entropy regularizer, right? So that this policy becomes more uncertain, right? So to encourage the exploration. With this simple addition, it can already lead to very interesting differences. Like say, once you learn the Q function in Q learning, right? As we said, you induce a policy from the Q function. Right? Every time, like say, you just pick the highest Q value action AT, right, to generate those token. But with this soft Q learning, you are actually applying a softmax function to normalize the Q value, and then you sample a token from this distribution. So you can see, right? If we recall that the architecture of conventional language modeling, right, or text generation, we said that every time step we generate a logic, right, and then we apply softmax. And then now in soft Q learning setting, we're actually kind of repurposing this logic of a language model as a Q values, right? So it's one of the fundamental differences compared to in supervised learning, right? You have a very different definition or interpretation of this output from the model, right? It's no longer logic that only care about this particular step, the property of tokens of this particular step, but now we see it as a Q values, which measures the expected future rewards of the future. Okay, so it's one of the key things here. And the second is that with these new configurations, the training objective, we can go beyond this temporal consistency, the classical equation, and use a more advanced property of Q functions, which is called path consistency. I will dive a little bit more details later. And this training really makes the this learning more stable and efficient. Okay, so a very quick introduction of path consistency. Again, this is something introduced already in the past for robotic control, but we cannot import these advanced techniques in text generation. This path consistency basically tells that this optimal Q function should follow this equation. Basically, you define a couple of other concepts, right, based on the Q function. So you have a more concise equation here. So with this consistency equation, again, you can easily derive this objective, right? Again, it's a regression problem, right? It's a regression target based on this equation, and you want to make sure that your induced policy from the Q function really satisfy this equation, right? So you will make this part as the regression target, and you train the induced policy accordingly, right? By minimizing the distance between the two values. So you can see, for people who are familiar with reinforcement learning, you can see, right, this part is actually the advantage of a particular state and the action. So again, we see the key difference from traditional supervised learning, like a maximum likelihood estimation, right? In MLE, we say this Q is the logic, right? And we're basically increasing the logic or the log probability of particular token AT blindly, right? We want to maximize it as much as possible. But in soft Q learning, we are actually matching this log probability of token AT with this advantage. So again, right, this property, this advantage take care of future possible rewards, right? So it's a kind of something captures more information, right? This is a very different training target compared to MLE, basically. And this training is fast because we have softmax here, right? So actually in this part here, you involve all the Q values of all tokens in the vocabulary. So every gradient will update the Q values of all vocabulary tokens. And there's a multi-step version of path consistency. You kind of derive from this single path consistency. I won't dive into more details here, but let's assume there's such a theory right here. And with this nice theory, you can derive a second objective, which is multi-step objective. Again, this is the regression target, right? Based on this part, and you want to train this policy to so that it can kind of like close the gap between this target and the policy value, right? And you can see here in this regression target, we directly use the non-zero final step reward as a supervision signal, right? So this makes the training more stable because you have the true training signal here. Okay, So this is the key idea of path consistency. Basically, you have these path consistency equations, right, and use that to derive the objectives as the regression target, as a regression problem, and you train this policy based on the objectives, right? It's okay, and interestingly, this implementation is very easy because we have correspondence between these Q values and the logic, right? That means you can simply reuse whatever traditional language model architectures, right? You can generate, say, create a model and collect whatever like samples from model, or if you have data, right? You make them as the samples, right? And then you compute the Q values. Basically, it's exactly the same procedure to compute the logic, right? You can use Hugging Face library to compute the Q values, right? And then you compute the reward of the samples, and then evaluate the soft Q learning objectives, right? Those path consistency objectives, and do an update. Okay, so it's pretty straightforward. And then with this new algorithm, let's see, right, how it can really help solve those challenges in those interesting problems we have seen. So first setting is the learning from noisy or negative text. Here's a particular example, right? We want to generate we want to do entailment generation. Basically, given a premise, we want to generate a hypothesis that entails the premise. Okay, this, for example, you have this input as a premise. Hypothesis can be like, say, Sophia is outdoor, right, which entails this input. Or a negative sample is something like Sophia is inside her house, right? This actually contradicts with the premise. Okay. So the training data, we simulate this noisy data setting by sampling from the corpus some noisy pairs. Here, well, in these pairs, only 50% of the pairs are really entailment pairs. Other pairs can be neutral or contradiction. And the 20% of the pairs are actually negative samples, which means the output, the ground truth, the y, right, in the data is a contradiction to the premise. Okay, in this very challenging setting, we use the reward like the entailment classifier. We want to generate the hypothesis like maximize the classifier accuracy, like entailment accuracy, entailment probability. Right? So this is one reward. And we want to make sure the output, the hypothesis is fluent. So perplexity is another reward. And we found that a blue score with regard to the input premise can effectively prevent the triple generations. So we basically have this reward. With these three rewards, we just compose them together, right, with a weighted average, and then plug into the soft Q learning and train the entailment generator. Okay. So here are some results. You have maximum likelihood estimation and other different variants, like say data reweighting, right? Because you have some negative data, so you can apply some like negative weights to the examples, right? To do the training. Or you have like previous off-policy reinforcement algorithm, like GoldS, which is some algorithm proposed last year. But we can see in the results, right? Those MLE or like off-policy RL actually do not really work well because they rely heavily on the data quality. Okay, with these noisy and negative samples, it's very hard to train well using this algorithm. For soft Q learning, you can see, right, we kind of achieve much higher entailment rates, and the language is as fluent as MLE, basically. Okay, so this is the first application. When you have noisy negative training data, you can use the reward functions and soft Q learning to train the model of interest. And the second application, let's go back to this interesting problem, right, of generating adversarial attacks, for example, to an entailment classifier. Okay, we want to generate readable hypotheses that are classified as entailment for all premises. Okay, and here we use this most popular entailment classifier on Hugging Face as something we want to attack. Okay, so to train this entailment attack generator, basically we don't have any direct supervision data, right? Because we don't know any previous like successful attacks, right? So we don't have supervised data. we just use like weak data, like all hypotheses in an RI corpus. So that's basically the model knows the domain, right? So, but it's a very weak data. It does not tell you anything about the text. Okay. Reward, as we have seen, right, we can use the indeterminate classifier, indeterminate probability as one of the rewards, and the language fluency, right, to make sure the hypothesis is readable, and we include a couple other reward, like say we don't want the language to be repetitive, so it's a repetitive penalty. Okay. So previous adversarial algorithms are not applicable here because those algorithms were designed to attack for specific premise. And here we want to do more challenging thing, right? In universal attack where it attacks all premises. And other algorithms might also not be able to generate, readable attacks. So we do not compare with them directly. So before we go into everything, that I was result, let's see, listening question here. So here for NLI, right, this question, a Causal classifier is available. I wonder what would happen if when the final classifier is not as so good? Yeah, so this is a good question. Like in this entailment generation, right, this reward itself, right, based on the classifier, is kind of is noisy, right? So yeah, it's a good question. So let me see if I can go back. Yeah, here. So in this result, we are using a kind of a pre-trained NLI classifier. So we don't really assume this noisy reward signal, but yeah, I agree. Like I say, in practice, you may have these noisy reward signals. So yeah, we'll be happy to explore this in the future. So yeah, thanks for the question. So okay, so for this universal adversarial attack, let's see the performance, right? We compare with the other previous reinforcement learning algorithm like policy gradient, right? With MLE. Okay. So we can see, right? With this soft Q learning, you get very high indeterminate rates. Okay, and MLE plus policy gradient, it can successfully generate some successful attacks, but when you want to increase the diversity of the attacks, right, it tends to collapse. It cannot generate more diverse samples. So this is actually a very common issue in policy gradients, right? The model tends to collapse, even though you train in combination with supervised learning. Okay. And also, our algorithm can generate more fluent attacks, basically. And here are some very interesting samples that achieve very high attack rates. In soft Q learning, we learned that the person blah blah is blah blah. So this simple sentence successfully attacks like 97% of the premises in the test set of NLI data set. Okay, so this is the result of universal adversarial attacks. So the third application, prompt generation, right? As we have seen this, the problem is basically, right, given we want to learn a prompt generator such that given a topic, we can generate the appropriate prompt. So that with this prompt, the model can generate sentences of this particular topic. Okay. So we can see all this part as a reward function, right? We generate the sentences and we use the topic classifier as the as one of the accuracy as the rewards, right? And the complexity to measure the fluency of the generated sentence, and we combine both as the rewards. Okay. And again, our existing gradient-based prompt tuning, like previous tuning or prompt tuning from Google, are not applicable here because here we generate these discrete tokens, right? You cannot backpropagate the gradient directly, right? All the way back to the prompt generator. And also this prompt itself is discrete, right? So this prevents the gradient backpropagation. So we compare with previous couple of algorithms. This is still decoding, like plug and play language models of Zhiting, right? For people who already know this, right? Those are specialized algorithms for topic control used on like a pre-trained language models. Okay, but the accuracy is actually not that perfect. And we can see soft-skill learning achieves much better overall accuracy and fluency. Soft-skill learning, we can achieve like 90% accuracy using GPT-2. And the fluency is kind of comparable to plug and play language model. And overall, with this prompt control, we see that this prompt control is kind of better than the standard decoding. Whether you use soft-skill learning we proposed or traditional MLE plus policy gradient, you can successfully find a nice prompt. With this prompt, the inference is much faster, right? Because at the inference time, you just input the prompt and continue the generation with the standard decoding algorithm, right? But the plug and play and the Zhiting, they need specialized decoding procedures, which are kind of much slower, right? So this is the application of prompt generation. We achieve higher accuracy, fluency, and more efficient kind of inference. Okay, so a quick summary of this part. We see that we want to learn text generation from rewards, so that even you don't have data, you can still have other signals like reward functions to train the model. Previous RL, like policy gradient, low-Q learning, they suffer from those different difficulties, and soft-skill learning was proposed to make the training more stable and fast, so that you can really make these applications practical. And what's more, what's really interesting is that this soft-skill learning really opens up enormous new opportunities for us to integrating more advanced reinforcement learning techniques kind of already invented in robotics or other things haven't invented yet, right? One path consistency is one of the examples, right? We have been used in the algorithm, but there are other different things like replay buffer to further improve the data efficiency. Model-based reinforcement learning again is for improving the data efficiency, and high sides to make sure the training is more stable and faster. Okay, and with this new advanced, more stable training with rewards, you can really enable massive new application in text generation, right? Including prompt generation, adversarial attack, and there are many other different settings. Okay. Okay, so this is the first part. Next, I will quickly go through our other work, including in this one, where you have biased data, right? Like the gender and occupation bias. So with this biased data, how should we reduce the bias in the data, right, to train an unbiased model? So this is here we use a causal kind of modeling. So here, right, we consider this controllable text generation. Like given a text, we want to kind of like control the attributes of structure of the text. Right. So there are two core tasks, like attribute-conditional generation. Given a sentiment, we want to generate a sentence of this particular sentiment, or given a sentence, we want to do a style transfer, right? Say we want to change the sentiment from negative to positive. And there are a lot of applications like data augmentation, emotional chatbots. Okay. Common method for controllable generation, we see these two types as very different, right? For conditional generation, we have this conditional distribution, right? And textual step transfer, we train a model to model this particular distribution, right? And we have different method for training those distributions. And the machine learning based models typically only learn the correlation in the data because we only care about this standard distribution or marginal distribution or conditional distribution. Those distributions, right, only captures the correlations in the data and the inherent bias from the data, right? So corresponding to this causal ladder in causal inference, right? This basically is at the level of association where you capture the correlations, okay, instead of the causal relationships. So here in this work, we introduce the causal perspective into this controllable generation. We want to model causal relationships, not these spurious correlations between different concepts like gender and occupation, so that you can generate unbiased text using rich causality tools. For attribute-conditional generation, we formulate it as an intervention in a causal ladder, which introduces the dual operation that remove the dependency between attributes and confounders. I will have a little bit more details later. And for the text attribute transfer, we formulate it as a counterfactual inference, what basically asks the question, right? What would the text be if the attribute had taken a different value, right? Once we have this causal formulation of these two tasks, right, in this causal ladder, we can readily use, use for causality tools to make sure that you can remove the biases in the data. So the base of this formulation, right, is the structural causal model. Here is an example. You model this text as outcome, like say it's a restaurant review, and you want to control the sentiment of the restaurant review, right? So it's a treatment, and you have latent confounders, any factors correlating both treatment outcomes, like say the food type of a restaurant, right? So this is something you want to remove, right, from the generation, right? You don't want to correlate sentiments with food type, right? So you remove food bias, and you have this proxy, some additional information about the confounders, like you may observe food type of a restaurant review, right? So this proxy helps you to identify those confounders so that you can break this dependency. Okay, I'll skip this part. So for attribute conditional generation with this intervention, right, as a comparison, previously we care about this conditional distribution, which can be decomposed in this way, right? If you introduce this latent confounder here, you are basically marginalizing Z like this way. But with this dual operation, right, standard techniques in causal inference, we care about this interventional conditional distribution, which you can see the difference here, right? Here, Z is no longer depending on A, which is the attribute. So effectively, you are breaking this dependency between the confounder and the attribute of interest, so that when doing the generation, these two concepts will no longer correlate with each other, right? So you can generate unbiased samples based on the sentiment or attribute of interest. Okay, counterfactual for text attribute transfer is similarly you use the standard three-step procedure in causal inference. You first given an original sentence, you first infer this G and A, right? And then you perform the intervention by applying the dual operation. So again, these two the dependency here is kind of broken, okay? And then you predict new X given the Z and the sentiments of interest, okay? So I will skip the part of the learning, but with this kind of this structural model, right? You can still use the pretrained models, right, as the initialization for the generation part or the kind of like a variational part. Okay. So experiments, we kind of construct very challenging data sets with strong bias in the data. Like say in this Yelp customer review, most of the examples, like 90% of the examples, have this correlation, like sentiment sentiment is positive is usually about a food or restaurant. If sentiment is negative, it's usually about other type of items, not restaurant. Okay, so this is very biased data with strong correlation between sentiment and the restaurant. And the human biology data set is again a very biased data, like the gender and the occupation. We make the data very biased. Like she is always associated with nurse, and he is always associated with attorney. Okay, so let's see, right? With the causal formulation, how much we can reduce the bias in the data. Okay, so here's the results on Yelp data. We can see with traditional conditional distribution modeling, right? Like conditional language model, which is perhaps the most popular methods in practice we'll use, or other like steer decoding like Jedi, as we have seen earlier. you kind achieve certain level of accuracy, but the bias is very high. Basically, 70% of the outputs are still biased, right? With this association between, like say, sentiments and the restaurant. And we can see here, we cannot reduce the bias, right? 90% is the perfect unbiased output. So we'll achieve 50% is the perfect unbiased text. We achieve 59. And we have also get a higher accuracy, right? Because we break this correlation. So causal model basically improve the control accuracy and reduce the bias. Okay, and the biology is the same. We achieve this result. Human evaluation. Some examples we can see both negative and positive. We can successfully generate reviews for restaurants. Okay, similarly, text style transfer with the counterfactual inference, we obtain higher accuracy and reduce the bias, keep the bias pretty low. And the previous conditional models, they basically completely failed on this kind of biased data. Basically, it cannot successfully transfer the sentence. Okay, so summary. It's a causality plus machine learning is really a fundamental new techniques to not only for controllable generation, but also other perhaps other marginal NLP problems, like say dialogue summarization, right? How can we apply those causality formulation to those more complex tasks? And for understanding or reasoning, right? Say from a question answering, multi-step, multi-hop reasoning, how can we really capture the causal relationships between different concepts instead of just the correlations? Okay, so the last part is about evaluation, where we don't have references. We propose a unified framework, but I guess I don't have time to really dive into the details. The key idea is basically that when you don't have reference for evaluation, there are already a lot of different metrics for different tasks, right? So you have 100 tasks of text generation, you may have 1,000 plus different metrics for different evaluation. So can we have a more unified theoretical ground for this NLG evaluation, right? Text generation evaluation. We formulate a framework based on the information change between input and output. Like summarization is to compressing information from compressed information, right? So basically compression. Transduction is like machine translation is to convert information in a different format, but you want to keep everything, right? So it's the and you don't want to add anything. So it's a very flexible transduction. And the dialogue and the story generation, you want to create a new information, right? So different tasks have different goals in terms of information change, right, between input and output. So with this, we can pre-train an information alignment model, and with this information alignment model as an intermediate representation to measure different aspects of this task, like consistency, relevance, precipitation, and the groundedness. Like creating information must be aligned with external sources, like in grounded dialogue, right? So we show that this unifiedly designed matrix has much higher Coleman correlation consistently over many of the tasks. Like we compare all these different metrics for summarization, and our metrics has higher human correlation. Is on relevance of summarization, attribute transfer, and the dialogue, right? We want to measure the groundedness of the generated response. And the engagement is how engaging the outputs are, right? In a chatbot, right? So a summary, based on the information change and alignment that categorize the text generation tasks, we create this intermediate representation, which is the information alignment between input and outputs. And based on that, we design different metrics for different aspects and achieve very strong human correlation. Okay, so I'm running out of time. So I'm happy to take a couple of questions.
Thanks, Zhiting, for those introducing very awesome talks, very awesome works. Yeah, so I actually have one question before I ask my own question. So there's one quick question in the chat. So how did you measure the bias? That's relevant.
Yeah, so yeah, so every time when we generate an output, we'll measure, its we'll use a classifier to classify, say the gender of that output and the occupation of that output, right? And then we can measure the ratio, right? How much this gender and the occupation, are correlated with each other, basically. So 50% means that there is no correlation between gender and occupation. Is kind of half-half, right? So and the 100% means that they are fully associated with each other.
Yeah. Okay. So actually, the question I want to ask is kind of related to both your first part and the second part of the talk. So I remember in your first part, a part of the reward you use to generate the hypothesis is the blue score, which means that you are encouraging the model to generate some hypothesis which has a higher overlap as the given, generating a premise, so which is having a higher similarity as the higher overlap as the with the given premise, given hypothesis. But from another perspective, sometimes people will also argue that the overlapping between the premise and the hypothesis could be a shortcut feature which leads to spurious correlation in natural language inference, right? So I'm actually wondering, from the opposite perspective, is there a way to, let's say, incorporate the technology in the second part of your talk to encourage the model actually generate the premise which is having less hypothesis with the having less overlapping with the hypothesis, but that could lead to a fairer NLI model?
Yeah, this is a very nice question. So yeah, here we incorporate this blue score and actually its weight is very small. We found that it's very effective to prevent this collapse of this, or like generating triple generations. But overall, right, what you suggest, I think, is a very nice thing, like how those different techniques can combine to solve this problem, right? How causal inference can solve the bias in reinforcement learning, or like vice versa, like say in causal inference, right? In that part, we still need data, like to learn that causal relationships between different concepts. But here, reinforcement learning is a way that you don't really need the data, but using the reward function to do learning, right? So you can use reinforcement learning as a subroutine to identify those causal relationships. So yeah, I think those are very interesting parts. I think definitely something we can explore in the future.
Yeah, thanks, Zhiting. Yeah, I think we can probably discuss about that more when we having our one-on-one meeting. Yeah. So any other questions from the audience? Although we are just 1 or 2 minutes away from the end of this seminar. Yeah, I guess, well, since we are very close to 12 p.m., we can conclude the seminar at here, and actually many of us will continue to have one-on-one meeting, and that we can discuss a lot of the thoughts over there. But very thanks a lot, Zhiting, for giving this very informative talk. I really learned a lot from those awesome works you have done.
Yeah, thank you for joining. Cool. See you later.
See you soon. Bye.